You think gravity is a force. Of course you do. Everyone does. Something falls, you say gravity pulled it down. The Earth orbits the sun. Gravity keeps it there. An apple drops from a tree. Gravity did it. Newton told us this 300 years ago. Gravity is the force that attracts massive objects to each other. Simple, clean, obvious. Except it's wrong. Completely wrong. And Richard Feynman knew it was wrong. Einstein knew it was wrong. Anyone who has really worked through general relativity knows it's wrong. But here's the thing that should bother you. If gravity isn't a force, what is it? And if objects aren't being pulled by gravity, why do they fall? Most people have never seriously considered this question. They just accept the story they learned in school. Massive objects attract each other. The Earth pulls on you. You pull on the Earth. Newton's law of universal gravitation. That's gravity. Case closed. But that's not an answer. That's just repeating words. When you really ask what gravity is, when you dig into what's actually happening when something falls, you discover something so strange, so fundamentally different from every other force in nature, that it changes everything you think you know about motion, space, and the universe itself. Gravity isn't a force, it's geometry. It's the shape of space-time, and understanding that changes everything. Let's start with what Feynman would call the ordinary story, the one everyone knows. Drop a ball. It falls down. Why? Gravity. The Earth is pulling on it. Fine. Push a book across a table. It slides and then stops. Why did it stop? Friction. The table was pushing back. Fine. Tie a rock to a string. Swing it in a circle above your head. What's keeping it moving in a circle? Tension in the string. The string is pulling the rock toward your hand. Fine. In every one of these examples, there's a force. Something is pushing or pulling. And crucially, you can feel that force. When you swing the rock, you feel the string pulling on your hand. When you push the book, you feel the resistance. These forces are real. They're tangible. They're interactions between objects that are in contact or connected. Now think about gravity. Stand on a scale. It reads your weight. The Earth is supposedly pulling you down with a force equal to your weight. But here's the question Feynman would ask. Do you feel the Earth pulling you down? You feel the floor pushing up on your feet. You feel the scale pressing against you. But do you feel the Earth pulling? No, you don't. What you feel is the floor resisting, the floor pushing back, not the Earth pulling down. Now jump off a diving board. You're falling through the air. The Earth is supposedly pulling you down with enormous force, accelerating you at nearly 10 meters per second squared. That's a substantial force. If you weigh 70 kilograms, that's 700 newtons of force, equivalent to someone pushing on you with 150 pounds of force constantly. That should feel like something, shouldn't it? But what do you actually feel when you're falling? Nothing. You feel weightless, completely weightless. Skydivers report this. Astronauts in orbit report this. Anyone who has ever been in free fall reports the same thing. No sensation of being pulled. No feeling of force acting on you. Nothing. You feel exactly as you would if you were floating in deep space, far from any planet or star, with no forces acting on you at all. This should strike you as extremely strange. If gravity is a force, a real force like friction or tension, why don't you feel it when it's supposedly acting on you? Every other force you feel when it acts on you. Push on a wall, you feel it. Get hit by a ball, you feel it. But fall freely under gravity? You feel nothing. This was one of the key insights that led Einstein to general relativity. The realization that gravity doesn't feel like a force. It behaves differently from every other force in a very specific, very important way. Let me show you what Feynman meant when he said gravity is different. Take two objects, a hammer and a feather. Drop them in a vacuum where there's no air resistance. They fall at exactly the same rate. They hit the ground at the same time. This is Galileo's great discovery. All objects fall at the same rate regardless of their mass. Now, think about what that means. The hammer is much heavier than the feather. It has much more mass. If gravity is a force, then, according to Newton's second law, force equals mass times acceleration. The gravitational force on the hammer should be much larger than the force on the feather, because the hammer has more mass. But they accelerate at the same rate. How is that possible? Well, you might say, the gravitational force is proportional to mass. The Earth pulls harder on the hammer, but the hammer resists acceleration more because it has more inertia. The two effects exactly cancel. So everything falls at the same rate. That's the Newtonian explanation. And, mathematically, it works perfectly. But Feynman would ask you to think about what a remarkable coincidence that is. The force that the Earth exerts is exactly proportional to the mass of the object. And the resistance to acceleration is also exactly proportional to the mass of the object. And these two completely different properties, gravitational mass and inertial mass, happen to be exactly equal. Always, for every object, without exception, to incredible precision. We've tested this to 1 part in a trillion. Gravitational mass equals inertial mass exactly. That's not a coincidence. That's not an accident. When something works that precisely, when two apparently different things turn out to be exactly the same, there's a deeper reason. There's something fundamental going on. Einstein realized what that deeper reason was. Gravitational mass and inertial mass are the same because gravity isn't a force at all. Objects in free fall aren't being acted on by a force. They're moving, naturally, freely, following the straightest possible path through space-time. And the reason they all fall at the same rate is because they're all doing the same thing, following the geometry of space-time. The hammer and the feather fall together because they're both following the same curved path through space-time. Their mass doesn't matter because no force is acting on them. They're in free motion, natural motion. The geometry tells them where to go, and they go there. Now you're probably thinking this sounds insane. Objects fall because space-time is curved? What does that even mean? How can empty space be curved? This is where Feynman's approach becomes essential. You have to build up the idea carefully, step by step, using things you can visualize and understand. So let's start with something simpler. Imagine you're on the surface of the Earth, and you want to travel from New York to Tokyo. What's the shortest path? On a flat map, the shortest path looks like a straight line. But the Earth isn't flat. It's a sphere. The actual shortest path between New York and Tokyo is a curve. It's what we call a great circle route. Airplanes fly along these curved paths because they're the shortest distance across a curved surface. Now, if you were an ant living on the surface of the Earth, and you had no concept of the Earth being a sphere, you might think forces were acting on you. You'd try to walk straight, but you'd keep curving. You might invent a force to explain why your straight path curves. But there is no force. You're just walking on a curved surface. The straightest path you can walk on a curved surface is itself curved. That's what's happening with gravity. Space-time, the four-dimensional combination of space and time, is curved. And objects moving through space-time naturally follow the straightest possible paths through that curved geometry. Those paths look curved to us when we draw them in space, but they're actually straight in space-time. They're called geodesics, the technical term for the straightest path through curved space. And here's the key insight. When you're following a geodesic, when you're in free fall, you're in natural motion. No forces are acting on you. You feel weightless because you are weightless. You're not being pulled. You're not being pushed. You're just moving along the natural path that the geometry of space-time defines. The Earth isn't pulling the Moon. The Moon is following a geodesic through the curved space-time around the Earth. The Sun isn't pulling the Earth. The Earth is following a geodesic through the curved space-time around the Sun. The apple isn't being pulled from the tree. When it breaks free from the branch, it starts following a geodesic, which happens to intersect the surface of the Earth. No forces, just geometry. But this raises an obvious question. If objects in free fall aren't experiencing a force, what about when you're standing on the ground? You're not falling. You're not in free fall. You're standing still. What's happening to you? This is where the picture gets truly strange and truly beautiful. When you're standing on the ground, you are experiencing a force, a real force. But it's not gravity. It's the electromagnetic force from the ground pushing up on your feet. Think about it. Your feet are made of atoms. The ground is made of atoms. Those atoms have electrons. When you stand on the ground, the electrons in the atoms of your feet and the electrons in the atoms of the ground repel each other electromagnetically. They push apart. The ground is pushing up on you. That's the force you feel. That's the force that's stopping you from following your natural geodesic path through space-time. You want to fall. The geometry of space-time is telling you to fall, but the ground won't let you. It's pushing you up, preventing you from following your natural path. This completely inverts the usual picture. Normally, you think you're at rest and gravity is pulling you down, but actually, you're being accelerated upward by the ground, prevented from following your natural free-fall path. This is the equivalence principle, Einstein's great insight that Feynman loved to teach. The equivalence principle says that being at rest in a gravitational field is equivalent to being accelerated. Standing on Earth feels the same as being in a rocket in deep space accelerating at 1g. In both cases, you feel a floor pushing up on your feet. In both cases, if you drop something, it accelerates toward the floor. The experiences are identical because the physics is identical. In both cases, you're being prevented from following your natural geodesic path through space-time. The rocket is accelerating you through flat space-time. The ground is accelerating you through curved space-time. But the local experience is the same. You feel a force pushing up on you. And here's the crucial point. That upward push from the ground, that's a real force. That's the electromagnetic force. But the thing you call gravity, the thing you think is pulling you down, that's not a force. That's just the curvature of space-time trying to tell you which way your natural path should go. Let me make this more concrete with an example Feynman often used. Imagine you're in an elevator. The cable breaks. You start falling. What do you feel? Nothing. You're weightless. Now drop your keys. They float next to you. They don't fall to the floor of the elevator because both you and the keys are in free fall, both following geodesics, both moving naturally through space-time. From your perspective inside the elevator, there's no gravity. Everything floats. But from the perspective of someone watching from outside, both you and the elevator are accelerating toward the Earth. They would say gravity is pulling you down, but you feel nothing. You're in natural motion. Now imagine instead that the elevator is in deep space, far from any planet. And suddenly, rockets attached to the bottom of the elevator turn on, accelerating the elevator upward at 1 g. What do you feel? You feel the floor pushing up on your feet, exactly like standing on Earth. Now drop your keys. They fall to the floor, or rather, the floor accelerates up to meet them. From inside the elevator, it looks and feels identical to being on Earth. But there's no planet nearby. There's no gravity. There's just acceleration. Einstein's point was that these two situations are not just similar, they're equivalent. There's no experiment you can do inside the elevator to tell the difference. If you're in free fall, you feel weightless whether you're falling in a gravitational field or floating in deep space. If you feel a floor pushing on your feet, that's acceleration, whether it's the Earth's surface or a rocket engine. The force you feel is always from acceleration, from being pushed off your natural geodesic path. Gravity itself, the supposed force pulling you down, doesn't exist. Now, you might be thinking, okay, fine, but what causes the space-time to curve in the first place? If gravity isn't a force, what makes space-time bend around the Earth or the Sun? That's where Einstein's field equations come in. And this is something Feynman was careful to explain clearly. Mass and energy curve space-time. The more mass or energy you have in a region, the more that region of space-time curves. The Earth has mass, so it curves the space-time around it. The Sun has much more mass, so it curves space-time much more. And objects moving through that curved space-time follow geodesics, which we perceive as orbits or falling. But here's the thing. This isn't a force relationship. The Earth isn't exerting a force on space-time. The Earth is just there, existing, and its mere presence warps the geometry of space-time. It's more like how a heavy ball placed on a stretched rubber sheet creates a depression. The ball doesn't push on the sheet with a force. It just distorts the geometry of the sheet by being there. And if you roll a marble across that sheet, the marble will curve toward the depression. Not because the ball is pulling on the marble, but because the geometry of the sheet is curved. This analogy with the rubber sheet is famous, and Feynman would be the first to tell you it's imperfect. The rubber sheet is itself sitting in a gravitational field, which is why the heavy ball creates a depression. That's circular reasoning when you're trying to explain gravity. But the geometric idea is right. Mass curves space-time, and objects follow geodesics through that curved space-time. That's the essence of general relativity. That's why gravity isn't a force. Now, let me show you why this isn't just philosophical quibbling. Why does it matter whether we call gravity a force or geometry? Because the predictions are different. In Newton's theory, gravity is a force, and that force propagates instantaneously. If the sun suddenly vanished, the Earth would immediately fly off in a straight line. Gravitational force would disappear instantly across 93 million miles. But that violates special relativity. Nothing can travel faster than light. Information can't propagate instantaneously. In Einstein's theory, gravity isn't a force, it's curvature. And curvature changes propagate at the speed of light, as gravitational waves, ripples in space-time. If the sun vanished, the Earth would continue orbiting for about 8 minutes, the time it takes light to travel from the sun to the Earth. Only then would the curvature change, and the Earth would fly off. We've measured this. We've detected gravitational waves from colliding black holes and neutron stars. The waves travel at exactly the speed of light, exactly as Einstein predicted. That's not just a theoretical nicety. That's a fundamental difference between gravity as force and gravity as geometry. Here's another prediction. In Newton's theory, Light shouldn't be affected by gravity because light has no mass. Gravity is a force between massive objects. Massless photons shouldn't feel it. But in Einstein's theory, light travels through space-time. And if space-time is curved, light follows that curvature. Photons follow geodesics just like everything else. So light should be bent by massive objects. In 1919, Arthur Eddington measured the positions of stars during a total solar eclipse. The stars appeared slightly shifted from their normal positions because the light from those stars passed close to the sun, and the sun's mass curved space-time, bending the light path. Einstein's prediction was confirmed. Light was bent by the sun, even though light has no mass. That's impossible in Newtonian gravity. But it's natural in general relativity, because light is just following the curved geometry of space-time. This has become routine. We observe gravitational lensing all the time now. Distant galaxies appear distorted, stretched into arcs and rings, because the light from those galaxies passes through curved space-time around massive galaxy clusters. The geometry bends the light. No force required. Feynman loved to point out another consequence of this geometric picture: time. If space-time is curved, then time must also be affected. And it is. Clocks run slower in stronger gravitational fields. Not because some force is acting on the clock mechanism, but because the geometry of space-time itself is different. Near a massive object, space-time is more curved, and time passes more slowly. This isn't a mechanical effect, it's a geometric fact. We've measured this too. Atomic clocks at different altitudes run at different rates. GPS satellites have to correct for this. Time runs slightly faster for the satellites than for clocks on the ground, because the satellites are farther from the Earth, in a region where space-time is less curved. If we didn't account for this, GPS would give you the wrong position, off by miles within a day. This is real. This is measured. Time itself changes because of the geometry of space-time. That's completely foreign to Newton's picture, where time is universal and absolute. But it's natural in Einstein's picture, where time is part of the geometry of space-time. Now let's return to something more direct, something you can feel. You're standing on the ground right now, reading this. You feel the ground under your feet. You feel your weight. In the Newtonian picture, gravity is pulling you down with a force, and the ground is pushing up with an equal and opposite force. The forces balance so you don't accelerate. You're in equilibrium. That makes sense. It's intuitive. But in the Einsteinian picture, what's really happening? You want to free fall. The natural geodesic path for you through space-time is to accelerate toward the center of the Earth. That's the straight path in curved space-time. But the ground is in the way. The atoms of the ground are held together by electromagnetic forces. Those forces are strong enough to resist the tendency of the ground to follow its own geodesic. The ground doesn't want to collapse to the center of the Earth because electromagnetic forces hold the atoms apart. And those same electromagnetic forces push up on you, accelerating you upward relative to your natural geodesic path. You are constantly being accelerated upward at 1g. That's why you feel weight. You're being pushed off your natural path by a real force, the electromagnetic force from the ground. In freefall, when nothing is pushing on you, you follow your natural geodesic and you feel weightless. Standing on the ground pushes you off your geodesic and you feel weight. This inverts the entire picture. Freefall is natural motion. Standing still in a gravitational field requires a force. That's the opposite of the Newtonian view, where rest is natural, and free fall requires a force. But it's the correct view. It matches what you actually feel. In free fall, you feel no force. Standing on the ground, you feel a force, the upward push from the ground. That's real. That's measurable. That's what weighs on a scale. The scale isn't measuring gravity pulling you down. It's measuring the electromagnetic force pushing you up. Feynman would make this point very clearly. The force you think of as gravity, the thing pulling you down, doesn't exist. What exists is the curvature of space-time telling you which way to move naturally. And what exists is the electromagnetic force from the ground preventing you from moving that way. The sensation of weight is the sensation of being prevented from following your natural path. It's the sensation of being accelerated by a real force, the electromagnetic repulsion between atoms. Gravity itself is silent. You can't feel it. You can only feel the forces that push you off your geodesic path. Let me give you another example to drive this home. Astronauts in the International Space Station are weightless. They float. Objects float. They're in what we call microgravity or zero gravity. But that's misleading. There is gravity at the space station. The gravitational field is only about 10% weaker than at Earth's surface. The space station is only 250 miles up. That's nothing on the scale of the Earth's radius. If gravity were a force, the astronauts should feel almost as much pull as we do on the ground. But they don't. They feel nothing. Why? Because they're in free fall. The space station is constantly falling toward the Earth. But it's also moving sideways very fast, about 17,000 miles per hour. So as it falls toward the Earth, it keeps missing, falling around the Earth in a circle. That's an orbit. The astronauts inside are also in free fall, following the same geodesic path as the station. So relative to each other, they float. They feel no force. They're in natural motion. The fact that the orbit is circular doesn't change anything. They're still following a geodesic through curved space-time. From their perspective, there's no gravity. From our perspective, on the ground, we say they're falling, but they don't feel it. They're in natural motion. Meanwhile, we're standing on the ground, being pushed upward by electromagnetic forces, accelerating away from our natural geodesic path. We feel weight. They don't. Not because gravity is weaker up there, but because they're allowed to follow their natural path, and we're not. Now you might ask, if gravity isn't a force, why do we have all these formulas for gravitational force? Why does F equals G times m1 times m2 over r squared work so well? Why can we calculate trajectories and orbits using Newton's laws? Because Newton's theory is an approximation. A very good approximation for weak gravitational fields and slow speeds. In those conditions, the predictions of general relativity reduce to Newton's laws. The geometric picture and the force picture give the same numerical answers. But conceptually, they're completely different. And when gravitational fields get strong, or objects move very fast, predictions diverge. Newton's theory says the orbit of Mercury should be fixed. Einstein's theory says the ellipse should rotate slowly, precessing over time. The rotation is tiny, only 43 arcseconds per century. But it's there. It was measured in the 1800s, and no one could explain it using Newton's theory. Einstein calculated it from general relativity, and it matched perfectly. That's because the curvature of space-time near the Sun is strong enough that Newton's approximation breaks down. You need the full geometric picture to get the right answer. Similarly, in Newton's theory, nothing can escape a black hole if its escape velocity exceeds the speed of light. But Newton's theory doesn't actually forbid faster than light travel. It's an awkward patch. In Einstein's theory, black holes are natural. Space-time curves so much that geodesics all point inward. There's no outward path. Not because gravity is pulling so hard that nothing can escape, but because the geometry literally has no outward direction. All future directed paths lead inward. Light itself can't escape because the geometry won't allow it. That's a fundamentally different explanation, and it makes testable predictions. Black holes have event horizons, boundaries where geodesics change character. We've detected these. We've photographed the shadow of black holes. We've measured gravitational waves from black holes colliding, all consistent with Einstein's geometric picture. None of it makes sense in Newton's force picture. The difference isn't just academic. It's real. It's measured. Gravity as geometry is the right description of nature. Feynman loved to emphasize that this isn't just mathematics. This is physics. We can measure the curvature of space-time. We've done it. GPS satellites measure it every second. Gravitational wave detectors measure ripples in space-time. Atomic clocks measure time dilation. Gravitational lensing maps the curvature around galaxies and clusters. This is empirical. This is real. Space-time really is curved. Objects really do follow geodesics. Free fall really is natural motion. This isn't just a useful way of thinking about gravity. It's what gravity actually is. The Newtonian picture of gravity as a force is useful, and it's good enough for many purposes. If you're calculating the orbit of a satellite or the trajectory of a baseball, Newton's laws work fine. But they're not the deep truth. The deep truth is that mass curves space-time, and objects follow geodesics through that curved space-time. That's gravity, not a force. Geometry. Now, let's address something that Feynman would insist on. You might be thinking, okay, I can accept this mathematically, but I still don't really understand it. How can space be curved? Space is empty. What's curving? This is where language fails us, because we're trying to describe four-dimensional geometry using three-dimensional intuitions. Space isn't a substance. It's not made of anything. Space-time is just the collection of events and the relationships between them. When we say space-time is curved, we mean that the geometry relating those events is non-Euclidean. The rules of geometry are different. In flat space, parallel lines stay parallel forever. In curved space, parallel lines can converge or diverge. On the surface of a sphere, two lines that start parallel, say two longitude lines at the equator, converge at the poles. That's curvature. It's a geometric property. You don't need the sphere to be embedded in a higher dimensional space for that to be true. The curvature is intrinsic to the surface. Similarly, space-time doesn't need to be embedded in some higher dimensional space for it to be curved. The curvature is intrinsic to the four-dimensional geometry of events. And we measure that curvature by seeing how geodesics behave. If two objects start at rest relative to each other, and then their paths converge, we know space-time is curved in that region. That's what we call tidal forces. It's not a force in the usual sense. It's a manifestation of space-time curvature. Here's a concrete example. Drop two apples side by side. As they fall, they get slightly closer together because they're both falling toward the center of the Earth, and their paths converge slightly. That convergence is tidal effect. It's evidence of space-time curvature. In Newtonian terms, you'd say the gravitational force points slightly differently for each apple, toward the center of the Earth, so their trajectories aren't quite parallel. In Einsteinian terms, you'd say they're both following geodesics through curved space-time, and those geodesics converge because of the curvature. Same observation, different explanations. But the Einsteinian explanation is more fundamental because it works in all cases, including strong fields and high speeds, where Newton's theory fails. Feynman would also point out that you can feel tidal effects directly under the right circumstances. If you were falling into a black hole, you'd feel stretched along the direction toward the black hole and compressed perpendicular to it. This is called spaghettification. It's not because the black hole is pulling on your head harder than your feet, though that's the Newtonian way to describe it. It's because the geodesics for your head and your feet are different. They're converging rapidly because space-time curvature is extreme. Your body is trying to follow multiple geodesics simultaneously, and they're not parallel. That tears you apart. That's a real force, a stress on your body. But it's not gravitational force. It's electromagnetic forces inside your body, resisting the tendency of different parts of you to follow different geodesics. The curvature is trying to make different parts of you move apart. The electromagnetic forces holding you together resist. You feel that resistance as stress. The black hole isn't pulling on you. It's just curving space-time so extremely that geodesics diverge rapidly. Let's go deeper into something Feynman emphasized in his lectures. The equivalence principle is local. It says that locally, in a small enough region of space-time, you can't distinguish between being in a gravitational field and being accelerated. But over larger regions, you can tell the difference because gravity shows tidal effects. If you're in a box accelerating through empty space, objects inside all accelerate together. No relative motion. But if you're in a gravitational field, there are tidal effects. Objects accelerate toward the center of the source, so their paths converge slightly. That convergence is the signature of space-time curvature. It's how you know you're not just in an accelerated frame, but in a genuinely curved space-time. And that curvature is what we call gravity. It's not a uniform force pulling everything the same way. It's a geometric structure that makes geodesics behave in specific, measurable ways. When Feynman taught general relativity, he would stress that the mathematics captures something real about nature. The Einstein field equations relate the curvature of space-time to the distribution of mass and energy. They're not just abstract symbols. They're a precise description of how matter tells space-time how to curve, and how curved space-time tells matter how to move. Matter curves space-time. Curved space-time guides motion. That's the dance. That's what replaces the idea of gravitational force. Here's something that should solidify this. Why is gravitational mass equal to inertial mass? In Newton's theory, this is a coincidence. Two different concepts that just happen to have the same value for every object ever measured. That's suspicious. In Einstein's theory, it's not a coincidence. It's inevitable. There's no such thing as gravitational mass. Objects don't have a property that determines how strongly gravity pulls them. They just have mass, which curves space-time and resists acceleration. And because freefall is natural motion, not forced motion, the resistance to acceleration doesn't matter. Everything follows geodesics the same way. A feather and a hammer follow the same geodesic. A planet and a moon follow the same type of geodesic. Mass determines how much space-time curves around an object, but it doesn't determine how that object responds to existing curvature. That response is universal. Follow the geodesic. That's why everything falls at the same rate. That's why gravitational and inertial mass are the same, because there's only one kind of mass. And gravity isn't a force that mass responds to. Gravity is geometry that everything responds to identically by following geodesics. This is the beauty of Einstein's theory. It takes a mysterious numerical coincidence in Newton's theory and makes it a fundamental feature of the geometry of space-time. Feynman would also point out the deep connection between general relativity and the other great theory of 20th century physics, quantum mechanics. We don't have a complete theory of quantum gravity yet. We don't know how to unify general relativity with quantum field theory. But we do know that gravity is different from the other forces. The electromagnetic force, the strong nuclear force, the weak nuclear force. These are all mediated by particles. Photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force. These are quantum fields, and their quanta are force-carrying particles. If gravity were a force like the others, it should be mediated by a particle too. We call this hypothetical particle the graviton. But here's the thing. In general relativity, gravity isn't a force. It's space-time curvature. So what would a graviton be? It would be a quantum of space-time curvature, a ripple in the fabric of space-time itself. Gravitational waves are classical ripples. Gravitons would be the quantized version. But quantizing space-time is incredibly difficult. It leads to mathematical problems that we haven't solved. This is one of the biggest open questions in theoretical physics. How do you reconcile the geometric picture of gravity with the quantum picture of everything else? Feynman worked on this problem. He developed a formulation of general relativity in terms of fields and particles, trying to make it look more like quantum field theory. But even he couldn't solve the full problem. And one reason it's so hard is that gravity really is different. It's not just another force. It's the structure of space-time itself. And quantizing the structure of space-time is much harder than quantizing a field that exists within space-time. But here's what we do know. At low energies and weak fields, we can approximate quantum effects in gravity, and the predictions match observations. For instance, the uncertainty principle should affect the positions of particles in a gravitational field, and it does. We've measured quantum interference of atoms in gravitational fields. The atoms behave like waves, and those waves are affected by space-time curvature. The patterns match the predictions. At higher energies, near black holes or in the early universe, quantum effects should be important. We don't have a complete theory, but we can make educated guesses. And those guesses suggest that space-time itself might be quantized at the smallest scales. The Planck length, about 10 to the minus 35 meters. At that scale, space-time might not be smooth geometry, but something more discrete, more granular. But even if that's true, at the scales we can measure, space-time behaves as smooth, curved geometry. And the picture of gravity as curvature, not force, remains valid. The quantum nature, whatever it is, doesn't change the geometric character at larger scales. Now, let's bring this all back to something concrete. You, standing here, reading this. You feel the ground under your feet. What's really happening? The Earth's mass curves space-time around it. Your natural geodesic path through that curved space-time would be to accelerate toward the center of the Earth. That's not a force. That's just the geometric structure of space-time in this region. But the ground is in the way. The ground is made of atoms held together by electromagnetic forces. Those atoms push back against your feet electromagnetically. The electrons in the ground repel the electrons in your shoes. That's a real force. That force accelerates you upward at 1g, keeping you from following your natural geodesic. Because you're being accelerated, you feel weight. You feel the force, the electromagnetic force, not gravity. Gravity is the name we give to the geometric structure that defines your natural path. And the weight you feel is the electromagnetic force preventing you from following that path. If the ground disappeared, you'd fall. You'd feel weightless. Not because gravity suddenly appeared, but because the electromagnetic force disappeared. You'd be free to follow your natural geodesic. And that feels like nothing. That's free fall. That's natural motion through curved space-time. This isn't just semantics. This isn't just a different way of talking about the same thing. The predictions are different. The understanding is different. The mathematics is different. In Newton's theory, gravity is a force, instantaneous, acting at a distance, mysterious in origin. In Einstein's theory, gravity is geometry, propagating at light speed, arising from the presence of mass and energy, explained by field equations. The two pictures give different answers for extreme conditions. Strong fields, high speeds, dense matter. And every test we've done confirms Einstein. Gravitational waves travel at light speed. Light is bent by massive objects. Time slows near massive objects. Orbits precess. Black holes exist. All of this makes sense in the geometric picture. None of it makes sense in the force picture. So, when Feynman explained gravity, he was careful to distinguish the Newtonian approximation from the Einsteinian reality. Newton's laws work for everyday purposes. Use them to calculate trajectories, orbits, structures. They're simple and effective. But when you want to understand what gravity really is, you need Einstein. You need geometry. You need curved spacetime and geodesics. And here's the final piece that brings it all together. Why does matter curve spacetime? We have equations, Einstein's field equations, that tell us how. But why? Is there a deeper reason? This is where Feynman would tell you we've hit bedrock. At some point, the chain of explanation ends. We have equations that match reality. We've tested them extensively. They work. But we don't have a deeper explanation for why those equations are true. Mass energy curves spacetime because that's what the universe does. It's a fundamental property of nature. Just like the electromagnetic force exists because charged particles exist. Space-time curvature exists because mass and energy exist. We can describe it mathematically. We can test it experimentally. We can use it to make predictions. But we can't explain it in terms of something simpler, because there isn't anything simpler. That's what fundamental means. Bottom level. Nothing underneath. And that's okay. That's how physics works. We observe patterns in nature. We write equations that describe those patterns. We test those equations against new observations. When the equations work reliably, when they let us predict things we haven't seen yet, we say we understand the phenomenon. By that standard, we understand gravity, not as a force, but as the curvature of space-time caused by mass and energy. That's the deepest explanation we have, and it's spectacularly successful. So why is gravity not a force? Because forces act on objects, pushing or pulling them. But objects in free fall don't feel pushed or pulled. They feel nothing. They're in natural motion, following geodesics through curved space-time. The curvature is caused by mass and energy. The geodesics are the straightest possible paths through that curved geometry. When you follow a geodesic, you're not being acted on by a force. You're just moving naturally through the geometry of space-time. Forces only appear when something prevents you from following your geodesic. The ground pushing up on your feet. A rope pulling a satellite in orbit. A rocket engine firing. Those are forces, real forces, electromagnetic, mechanical, chemical. But gravity itself, the thing that makes objects fall, the thing that keeps planets in orbit, the thing that bends light around stars, that's not a force. That's geometry. That's the curvature of space-time. And understanding that changes everything. It changes how we think about motion. Natural motion is free fall. Resisted motion requires a force. It changes how we think about space and time. They're not separate. They're unified into space-time. And that space-time has structure, geometry, curvature. It changes how we think about mass. Mass isn't just a quantity that resists acceleration. It's a quantity that curves space-time. And it changes how we think about the universe. The universe isn't a stage where forces push objects around. The universe is a dynamic, curved, evolving geometry, and objects move along the natural paths that geometry defines. This is what Feynman wanted people to understand about gravity. Not the formulas, though those are important. Not the calculations, though those are necessary. But the conceptual shift. The realization that what we call gravity is fundamentally different from what we call forces. It's geometry. It's the shape of space-time. And once you see that, once you really understand it, you can never go back to thinking of gravity as just another force. You see apples falling, and you know they're following geodesics. You see planets orbiting, and you know they're following geodesics. You see light bending around the sun, and you know it's following geodesics. Everything is following the geometry. And that geometry is determined by the distribution of mass and energy. That's gravity. Not a force. Geometry. Not comfort. Not the familiar Newtonian picture. Truth. The geometric truth that Einstein discovered and that every test has confirmed. Gravity is the curvature of space-time. Objects follow geodesics. Free fall is natural motion. Weight is the force that prevents you from falling. And that's not just a way of speaking. That's the structure of reality.